Alright, so stoichiometry. We're going to talk about molar masses and all that good stuff that you guys love so much, and the limiting reactants and concepts that go with that. Okay? So, the concept here with stoichiometry is to determine how much of something you should end up with, or how much of something you do need to carry out a reaction. One of the things we're always concerned with is not to produce a whole bunch of toxic compounds that we don't want to, right? You try to minimize the amount of toxic stuff you want to form. So for that, you need to know, well, how much do I start with? How much do I need? How much will I end up with? What are my byproducts, right? You need to be able to do the reaction. You need to be able to look at the numbers. And you can't count atoms, obviously. The only way to count atoms is by mass. You have to take the mass of your atoms. So, we're going to study the quantities. Yeah, we'll do all that. Okay? So, we'll talk about average mass of the objects is required to count, right? And chemist deals with the samples of matter. And there's something called a mass spectrometer. Okay? Looking at this is to kind of try to split them as much as you can to try to figure out, you know, like in an isotope setting, you want to know what the purity is, right? If you have a combination of them. So you have this little instrument where you put in the sample and it heats it. It vaporizes the sample. You have positive ions that are going to go through. You have ion accelerating electric field, ion beam, and then what happens is it's basically there's a magnetic field and it's splitting the least massive ions from the most massive. Okay, so that you can get a reading. It'll look like little lines, and then you will know about the mass based on the purity of the sample.
Are we doing that?
Oh, we're not doing that, but we will be looking at the results of the mass spectrometer. But we don't have a mass spectrometer.
That's something.
Amount of path deflection depends on the mass. Massive ions are deflected smallest. Because they're heavy, they can't deflect as much as the least massive ones, right? So heavier ones are going to deflect less. Positive, where the ions hit the position where it hits the detector plate provides accurate values. So you actually get a reading of where they hit. Where they hit has to do with their rate of deflection, their angle of deflection. Their angle of deflection is based on their mass. So you're kind of going round and round and trying to figure out, oh my God, what is the mass of this thing and how many of them are there, and you know, what the percentages are. So it's not an easy task. But all we do is look at the results to determine. So, average atomic mass. When you look at the periodic table, you see carbon has 12.01 it's 12.01 grams per mole, right? Where in the world did that 0.1 come from? There's no 0.1 proton, right? There's no 0.05. It's an average, but it's a weighted average based on the relative abundances of the isotopes on Earth. Okay? And that's not an easy task to do. Because think about it. Relative abundance of an element on Earth. Basically, you have to determine what percentage of this element is on Earth in this isotope. So in other words, every time we find carbon, 99.9% of the time we find carbon-12. 0.05% of the time we find carbon-14. So if I'm looking for carbon and I'm taking carbon off, you know, out of Earth, out of 100 times, only about, 5 times is going to be carbon-14. Okay? So carbon-12, 13, and 14 are my 3 isotopes of carbon. Okay? So how am I going to find the average atomic mass of carbon? Remember we did this? Isotopes are elements, same element, different mass number. Okay. So carbon-12, carbon-13, and carbon-14, what's the difference? They all have 6 protons. Carbon-12 has 6 neutrons. Carbon-13 has 7 neutrons. Carbon-14 has 8 neutrons. Okay? Then you're looking for abundance. Abundance means what is the percentage that we find carbon-12 on Earth? 98.89% of the time, we find carbon 12. 1.11% of the time, we find carbon 13. Carbon 14 is in trace amounts, so they don't even bother with it. So how do I get an average from this? I can't add 12 plus 13 divided by 2, right? That average isn't going to work. Why not? That would assume that each one is 50%. Is that the case?
No.
No? So what do you expect the average atomic mass to be? About what? About 12. Do you expect it close to be 13 at all? No. You're only dealing with 13 about 1.11%. Right? Like, if in a class your tests are 50% of your grade, but homework is 5%, right? You don't worry about maybe failing a homework, but you really stress out about failing a test, right? Because that has a bigger weight. And that's what this is. Carbon 12 has pretty much taken over, right? So 0.9889 is the 98.89%. That's 12. The mu is AMU. We're not going to use mu. It's going to be grams per mole for our purposes. 1.11% times the 13, right? You add them up and you're going to end up with 12.01, which is what you find on the periodic table. Okay?
And all of that information is given to you like in a question?
Yes.
Okay.
Pretty much. Yeah, all of it. Except obviously the end result. So, that's the mass spectrometer. You see why we don't have one, right?
Oh, wow.
You kind of get an idea of what that looks like. And the cost, is
more
not-
than this.
not in
our budget. It's definitely not in our budget, guys.
What do they use it
It's,
for?
again, you're only going to use it to determine the isotopic composition of naturally occurring elements, which is definitely not something we need to ever do in a regular chemistry classroom, AP, even AP, you don't even do it in college. You don't even see mass spectrometers until you get to your usually master's degree, or unless you're in a college that is all for research. You might see it in the lab here and there, but nothing that you would ever work on unless you're doing a thesis in that.
It looks insane.
Have you ever worked on?
Did you know how to work it? Like if it was in front of your face?
Not that one. There was another kind that's separated based on something, and that one I've seen and worked with. But they're difficult. Let me tell you. All right. So let's say here we have this one you need a calculator for, obviously. You have 4 isotopes of different mass numbers, obviously, with different compositions. So go ahead and find the average atomic mass, please.
With all of them?
With all of them. Yeah, this is all of them. So it's all of these.
So with this, let's say
You do-
like a multiple choice question.
No. But what the multiple choice question would ask you is this. Looking at this, but it would be a little bit more obvious, you could predict around where your average atomic mass would be. Like I could say this is going to be maybe closer to 206, between 206 and 207.
Okay. So
Let's say something like that, right?
0.014 times 2, is that how you would do it?
0.014
Yeah.
times the 203.973 plus
Okay.
0.241. Yeah. That. So you're going to take, right, the percentage, divide it into decimal, multiply with the mass number, and add it to the next one. Does that make sense?
There should only
Wouldn't
be
it-
1 0 after
Yeah,
the
wouldn't it
decimal
only be
point.
0.01?
Just 0.01.
Oh, it's 100, right?
That's so confusing. It's like, what do I do?
1, 2, 3.
And so on. Okay? Do that and get me an answer.
Yeah, I didn't do this right. Should I divide it by 4 afterwards?
No.
How do you know?
No.
If you're getting the percentage.
Since we're multiplying with the percentage, we just add it. There's no division afterwards.
Should we not round till the end?
And then use your sig figs. And in this case, oh good lord, they give you enough sig figs to work with. What'd you get? Any answers?
I had 2,506.
Oi, oi.
Wrong.
Yeah, you're off.
I
You're off on your thousands there. Maybe you forgot to.
Fourth time in
convert.
2 weeks.
have my SAT tomorrow.
Yeah.
The SAT.
My friend has the test tomorrow.
Yonatan? You have an answer?
Mr. how realistic would taking the chem subject test be in October?
October?
Pushing it. What about November?
Better.
In chems, the subject has
207,
different than the AP.
21.21. Oh no! Once you
multiple
cover
choice.
everything for the AP, you've already covered everything and more for the
So you're
subject
great
test.
for the subject
I
test.
got, because in bio it was so different.
I
the
got
subject was
207.2.
Yep.
for the bio.
To a 7.2, which means it is lead.
Actually.
Okay?
Yeah. That is fun. would
I
like
got
more
it.
of those.
Haha.
Good.
That one
I
was
just
fun.
Put
Easy math
9,000.
is fun.
Okay, so now look at the graph there. That's what the mass spectrometer gives me. When a sample of natural copper is vaporized, that in itself is not an easy task. Vaporizing copper. Takes a lot of energy, right? And then it's injected into the mass spectrometer. The results of the graph are shown there. You see that 69.09% of the time you have a mass number of 63, and then 65% of, sorry, 30.91% of you have mass number 65, right? So this is the relative abundance, which means it's percentage on the y-axis, and mass number is on the x-axis. So you do the same thing you did before. We don't need to do that. But I can show you what it looks like. Where are we going with this? Here we are. This is where we're going with that. Oh, is that number of atoms? I thought it was a percentage. It is a
Why didn't we
percentage.
do split last year? Like in November. Right?
Second semester.
Really?
Yeah.
What do we do all year?
Okay. So it gives you percentage. You get, because it's at 100, right? Otherwise you would have to get percentage, and that's what you get. Which is the...
What do we do first semester?
Whatever it was hard.
No, it was just
Okay.
a shock. I never did anything like that.
Number of moles and Avogadro's number, you
Oh,
already
really?
know. Avogadro's number is on the sheet that I will give you.
Do they give you any constants on the test?
Yes, whole bunch. And so a mole of a sample of copper looks like
That's
that.
pretty.
But iodine is obviously, depending on, but look at how much mercury you get for 1 mole of mercury, right? Because it's a lot heavier. And aluminum, like you need just 27 grams for it to be a mole. Copper, you need 63.55
Sulfur
grams.
white or yellow?
Huh?
It's yellow.
Sulfur is yellow. It's a yellow powder.
Are we doing a flame test on Tuesday?
No, we're doing something.
Flame test.
Remember with the colors?
That's like a whole nother chapter.
Okay. So this is just critical thinking. You can do that on your own time.
That's it?
Unfortunately, we don't have
Wait,
that.
we
kind
have
of-
double period on Tuesday.
Yes.
Tuesday. No class on that.
Oh, this
What?
Tuesday. I thought you meant no.
Yeah, I'll stay.
Okay. Moles and mass, and I think all of you have done molar calculations, so we're just gonna do some problems. But we are pretty much out of time, aren't we?
We have to drive straight from Allen here on Tuesday. She made it 20 minutes later.
Okay.
Say
So
20 minutes later?
Tuesday is going to, we're going to start at 9. It's going to be until 11:30 or so, I think. Somewhere around there. What? Okay. So it's, or,
That's a lab day, right?
yeah. It's going to be, so I'm going to do some stoichiometry in the beginning. And then we're going to move on to lab.
And we
Okay.
don't have you on Monday?
No.
No.
Okay.
Urgently.
Tuesday.